Okay, so basically just started Unit 6. The only thing I've introduced so far in Unit 6 is collision theory. This idea that as we start examining the application of chemistry at a macro scale, as we start specifically focusing on how to manipulate the rate of reaction, um, we have only really covered, okay, well, how at the particle level does it actually make sense that a reaction occurs? And why does it make sense that we can change the speed of a reaction occurring through various factors, such as temperature, surface area of solids, grinding it up more, creating more surface area, catalyst, which is the most effective, and what was the other one? Catalyst, temperature, surface area. Stirring. Thank you. Agitation, stirring. So that's kind of really all we've looked at. And we had you guys do an animation or audio PowerPoint, which I do want audio explanation of how the demo I showed you, we could explain it using collision theory. But that's not really a sufficient analysis of kinetics and the relationship between energy and matter. Because essentially what we're really looking at is the energy of a reaction in all forms, at the micro scale particle movement form, and we're going to eventually transition to the heat form today. How about energy as heat? Okay. So we are going to start looking at that. And to do that, I'm going to do this kind of bridging activity known as the hand boiler demo. And it's not a real intro because originally last year I did it as an intro to kinetics. I'm going to do it more as an intro to heat in kinetics today because we've already talked about kinetics. So we're going to kind of go backwards a little bit in terms of reground ourselves in the curriculum of your class. And one of the main topics or one of the main themes of this class is that you work with systems and models. Now, systems, we've already kind of defined. Does anyone remember what a system is? Like, how would you describe a system? Business-wise, mechanic-wise, how would you describe what a system is? What would you say the definition is? Yes, Aislinn? It's like a functioning order of operations. Yeah, it's a functioning order of operations, or a little bit more let me put it this way, actually, not more scientific, more general for the scientific community. It's a group of interacting components that work together to accomplish one thing, some common task. So this kind of goes backwards, by the way. This is like a unit 1 review, but it's really important for us to remind ourselves of this common theme of science that's going to be particularly valuable as a background preface when we talk about the new stuff. So a system, just in case you don't remember, is a group of interacting components that work toward one task, like right toward one task or one goal or one function, right? They're all part of one kind of thing. They're not just group of interacting components that do everything separately and don't have any impact on each other. They have an impact on making that system work. So we're a system. We're a system of 27 students and one teacher and 2 TAs that work together to accomplish a common goal. Maybe you don't agree with the goal, but the goal of learning chemistry, right? So and the way that we define a system is we often have kind of this model. We use a model to kind of articulate and illustrate the components and the way that they interact as a system. The model that we tend to use is this very basic model of input, mechanism, and output. Input, what are the things, the components starting it all? Okay, what's the mechanism of how they interact in the system, and what's the end result, the output? Okay. And what we're going to see is we are going to look at a system that highlights the relationship or the mechanism or the interactions between energy and matter. particularly heat energy and matter. So this is a cute little toy from Japan, and it's Valentine's Day themed, which is adorable. And what we're going to do is input wise, what do we have here? Input wise, and here's just a little shot for the camera. Okay, what do we have here? What do you observe? Huh? Yeah, some type of liquid. You don't really know if it's oil, but some type of liquid. It's got a good viscosity to it. What else?
A glass case.
Yeah, a cute little glass tube, or what you think is glass. Yeah, excellent. Okay, so input wise, on the top half, okay, write what you see. Doesn't have to be detailed, just write what you see. So I think we said so far a liquid that's green. And what appears to be a glass tube of some sort, a glass container or glass tube of some sort. Now, what if I tell you that this system isn't just this glass? Because remember with systems, we can define what we call a system. I could say a system is just you two working and your partners. Or I could say a system is the entire class. Or I could say the system is the whole school. We define the boundaries of the system. That changes how many components that we have to address when describing how they interact. So what if I tell you this? Now, this system is with my hand. What would you include as input? My hand. So I would write that down because that definitely is going to matter. And if you're noticing something, something's happening. Okay, so now we're going to try to figure out the main goal of a chemist is not really the input and the output, because the input and the output is observable to any old Joe on the street. It doesn't take a genius to figure out what started it, what it ended with. The real trick as a chemist is, what is this transformation? What is the mechanism, okay, of how this works? The how this works part. We're going to try to define this based off of previous knowledge of collision theory. But collision theory isn't going to be sufficient. It's just going to help us be a launching pad on getting it going. So the real question is, how does this work? Because now let's look at the output, because it's a little hard to define how it works unless we see what it ends with. But let's switch to camera. Oh, look. Me. Okay. Shh. It's okay. So what we have here is our, okay, hand boiler. The system is the glass and my hand. What's the output? Doesn't just go to the top. What else does it do? What else does it do? Mm-hmm. That's not the output. That's the mechanism. That's how it's working. The output is, what have you physically observed? What's the result? Write down your output. Let's see, I think the green is a little harder to see. Let's switch over to a different one, different color. They're all different themes. They're so cute. Would anyone like to try and see if they can get it to boil more than me?
If you were to put hands on both of the
Ends?
ends, would it explode?
Oh, I don't think about that. Let's just see. I put ends.
Put it in between your armpits.
Hmm?
Put it in between your armpits.
Between my armpits.
Yeah, it's warm.
I'm good. Doesn't look like it does anything. And gravity takes over at that point. Mhm. Okay. Let's quickly switch over to notability. So what was the output? Too many words. What was the output? Liquid moves. Doesn't mean top. I also put my hand up top and it moved down. So liquid moves. And not only it moves, what does it do? It boils. And now it wasn't a vigorous boil. It wasn't like nonstop, but it definitely boiled. Or you saw bubbles at least. So liquid moves. Okay. You could put in opposite direction of hand placement. Okay. And then liquid boils. Okay. That's your output. That is your observable result. That's an output, is the observable result. Okay. Your input is the components involved. Now, the real question is, though, what's the mechanism? So to get us started, all right, just right from what you know about collision theory, okay, how you might explain why this makes sense. And then take the hint that Mika offered, which is it probably has something to do with heat as well. That's the new part. That's the additional part. So just take a moment to draw out some illustration and write a 1 to 2 sentence explanation of how this is working. How is it possible that the liquid moves? And how is it possible that we see boiling? So give it a shot. All right, so for mechanism, using your collision theory knowledge, what could you immediately say? Why this works, how this works? Aislinn. Okay, so based off of collision theory, we know that temperature increase, okay, leads to kinetic energy increase or motion of the particles, okay, which would make sense then when I add my hand, okay, is somehow increasing the temperature of the liquid. Okay, what else?
Maybe it heats up the gas, which pushes the liquid up.
Well, we don't have any gas in the beginning.
Or like the air.
The air, maybe it heats up the air, but the air is on top. So why would it push up the liquid? Like you're right. But if it just heated up the air would continue to stay up top and not, the air would have to be a pocket of air below. Okay, so there's something else that you probably need to notice about this. Collision theory is super helpful for understanding how particles work. We used it in the context of a chemical reaction, but is this a chemical reaction? No, this is not a chemical reaction. It's a physical. I'm just going from liquid to gas, boiling. So collision theory gets us going on this, but it's not really the best explanation for why this process is occurring. It gets us there, but what we really want to latch on to is the word that you guys keep on saying, which is heat. Heat. It has something to do with the heat transfer from my hand to the liquid particles, which we know from collision theory impacts motion. But the other thing to understand is just because I add heat doesn't mean I always get boiling. Like just because I add heat to water doesn't mean I actually get a boiling water. Sometimes you just get hot water. Okay. So the other thing that we probably need to start asking ourselves is, how do we define the amount of heat to go from the true liquid to gas, right? How do we determine what's the process for garnering enough heat to go from liquid to gas? And what does it really mean at the particle level to go from liquid to gas, to go from a warm liquid to a boiling liquid, a liquid that is producing gas molecules at a vigorous level? Okay. So mechanism wise, you might have drawn something like this little tube. Okay. And oh God, I am not an artist. And a hand. Lord help us all if I ever become an artist. And you might have drawn something like heat being transferred. Maybe that would have been like a preschool sketch for a preschooler to understand. It's the start of it. Okay. But then that leaves us with one, a very bad drawing, but two, a lot more questions to ask. So what were some of the questions that you guys realize that you need to ask in order to really understand what's happening here? Not just kind of understand, but what would be some of the questions that we needed to answer? Yes.
Boiling temperature.
Yeah, what is the boiling temperature or the boiling point of the liquid? What else might we need to answer to fully understand why this process occurs with just our hand? Yeah, or another way to put it is how much heat is actually being transferred? Is actually involved? What else might we need to ask ourselves? So activation energies with the chemical reactions, we're not making a new substance, but I think what you're probably saying is maybe that's leading us to something else. We're not having a chemical reaction, a new substance being made, but we are having the particles change state of matter. So maybe the question that kind of is parallel to that is, what does it take to change states of matter? How much heat is actually necessary to change states of matter? So maybe we need to ask ourselves, what does it really mean to change states of matter? Another kind of obvious question is what? Anyone? We kind of hit it with the first one, but it's go even more obvious than that. Yeah, what's the liquid? What's the liquid? Because understanding what the liquid is, understanding what the liquid is also impacts how we understand what's happening at the mechanistic particle level. Because like if the liquid's oil, that might change how we describe what's happening. But if the liquid is like water, that's a new question. When I hold water, it doesn't boil. So what's the liquid? A lot of questions we need to ask ourselves. And particularly, there's one that we also should ask ourselves is, which is the big idea, is what is the relationship between heat and matter? Heat, energy, and matter. Like, why are those things connected? We know they're connected just from living everyday life, but why is that true? How is that true? That's what we're going to answer in a very preliminary way. You really want to get into this, study thermodynamics at the collegiate level and post-grad. But we'll do an introductory level of understanding some of the concepts that help us explain this. What are you trying to understand? Second line, pink line. How much heat is actually involved? Yeah, of course. Okay. So once you have this written down, let's switch over back to unit 6 notes. Unit 6 notes. Okay. So we're going to start answering this question by introducing chemistry or the heat of chemistry. Chemistry is the study of heat in chemistry and energy in chemistry is known as thermodynamics. Okay. The first law of thermodynamics, does anyone know that from physics? First law of thermodynamics? Don't overthink it. Roman, do you know it? Huh? That is the first, that is not it. That's the first law of motion. Thermodynamics is also known as the law of conservation of energy. Okay. It tells us that energy is neither created nor destroyed. Now, energy obviously comes in various forms. We have kinetic energy and we have multiple subcategories of energy that fall under kinetic. Drea, phone. Are you doing your notes? Okay. We have multiple forms. We're going to be focusing on heat, which is a form of kinetic energy, motion kinetic energy, and chemical energy in this unit. That's going to be the forms of energy that we focus on. But it's really important just to preface that whenever we talk about energy, this law is still in action, and it's going to be particularly relevant for the lab that we'll do next week. Okay. Oh, and by the way, this unit 6 assessment is lab-based. You're actually doing a lab as part of your assessment. Okay. So the first law of thermodynamics is energy in all of its forms can neither be created nor destroyed. And if you already know this, don't write it down. But it can be transformed. Or another way of putting it is converted. It can go to a different version. So like we know from 8th grade that kinetic energy can become potential energy and potential energy can become kinetic energy. Okay. Also known as the law of conservation of energy. Okay. So kinetic is one of the big, or mechanical is one of the big categories of energy. For us, we care about kinetic energy in terms of motion and temperature. That's kind of our focus, as well as heat. That's kind of our focus as chemists. And then potential energy is all about the position or arrangement. Okay. Potential energy is all about position or arrangement of whatever you're looking at. So for us, it translates to what we call chemical or bond energy. That's kind of what we focus on in chemistry. This is our understanding of how we apply the concept of energy. So chemical energy is the energy, okay, due to the particular arrangement and bonds made between atoms. Okay. It's the energy due to the particular arrangement and bonds made between atoms. It also can include the energy due to the result of particles in motion. It's kind of a generic thing. I'm going to take the highlight of it's, we're going to particularly reference it in terms of the arrangement and bonds. So that means we at this level of chem are going to treat it as pretty much equivalent to another term known as bond energy. Bond energy is indicative, or it kind of points us to the energy, quote unquote, stored in the bonds. Okay. Now, stored is not a great word, to be honest, but it's sufficient for now. Okay. It's a little conceptually more friendly. So when we think about energy transformation in a chemical process in general, okay, let's go back to chemical processes, new substance making. Okay, when we think about that, step 1 is you have, okay, particles with high kinetic energy, right, necessary to reach activation energy, and a preset or a starting amount of potential energy due to the bonds, like the old bonds, right? So not only do you have kinetic energy present through its motion of collision, but you have some potential energy due to the fact of you have some arrangement of particles. Like you have a CO2 colliding with another molecule. That CO2 has a particular arrangement of the atoms in space with a particular double bond or single bond, right? That already comes in with energy. Remember how I said in the analogy that activation energy is the point from where you start to where you need to go? Your starting potential energy is based off of your starting bond arrangement. And then you have for overall energy, the additional kinetic energy that's due to the motion of the particles. Okay. Step 2. Okay. In order to bond break and bond reform, you collide, creating, what do we call that unique temporary compound? Do you guys remember that unique temporary compound that happens through the smashing of particles that last like a nanosecond? The point where you simultaneously bond and break and reform. What do we call that unique arrangement?
Activated, okay.
Yes, they collide, creating the activated complex. Okay, which, okay, is a high potential energy arrangement. There's very little motion happening at this point. It's kind of like you wouldn't say that when someone smashes up against a window in hockey, that they have a ton of motion happening at that moment. What they do have, though, is a huge, tense, okay, arrangement. Their face pressed against the glass. That's a high tension arrangement. High tension is like another way of saying high potential energy. So what we see here is we see most of our kinetic energy get fully transformed into potential energy. Okay. And then 3, okay, the particles continue moving in a new bond arrangement, which means you have a new value for potential energy. A new potential energy connected with those new bond arrangements. And of course, you get back some kinetic energy. You see that some of that energy is transformed back into kinetic energy to continue the motion of the particles, so they can continue colliding and moving about in space. So what you see here is you see a journey of energy, not just particle matter, but energy between that matter. So what we do then is, how do we graph this journey? We use a diagram. A picture's worth 1,000 words. Why explain all of that when I can just draw it? Okay, and by the way, this is totally going to be part of your quiz here. This is a big quiz topic for Friday. Okay, it's reading and drawing these potential energy diagrams. So potential energy diagram illustrates the journey of a chemical reaction in terms of energy transformations. And particularly, we're going to focus on from the perspective of potential energy, hence why we call it a potential energy diagram. We're going to just look at it one direction, because it's kind of like, if I know that there's a set amount of energy, law of conservation of energy in a system, in a mechanism happening, and I know that I have this amount of potential energy, that means whatever is remaining in the total is kinetic. So you can kind of piece together the potential and the kinetic part without having to graph both at the same time. Okay, so that's what we do. We isolate it. Okay, so the components for a potential energy diagram that we're going to focus on is the starting. Actually, I'm going to use this word. The potential energy of the reactants the potential energy due to the particular bond arrangement of your reactant molecules. Your activation energy is another one that we're going to really focus on. And I see that my handwriting gets incredibly worse as the year goes on. Oh my. Nope, that wasn't any better. Activation energy. And then the potential energy of the products. This is going to be the three main points that we highlight. So don't forget, when I say that activation energy is the difference between the starting, where you start and where you have to go, the highest point, what that translates to is on this graph, how would we write the equation to solve for it? It would be that the activation energy equals the potential energy of the activated complex, the highest hill. Ooh, Bessie. Minus the potential energy of the reactants, the distance I have to climb up. So here the activation energy is this distance. Whatever distance in potential energy amount that equals is the activation energy. From where I start to where I need to climb up. Now, what we look at is when we compare the overall journey, it's kind of nice to know, did I overall wise travel, if you're going to take the analogy of the distance, did I overall end up in a new location or did I end up at the same elevation, right? So when you look at the journey of a reaction, what we do then is we also not only compare where I start to the highest point I have to climb, but where I start and where I end. So when we see that when we compare the potential energy of the overall process, okay, and I'm actually going to write it like this, and I'm going to explain in a second what this means, okay? When we look at the overall change in the energy of the process, and we see that the products, the potentially energy of the products minus where I end, minus the potential energy of the reactants where I begin, where I start, is equal to a negative number. What that tells me is I end in a bond arrangement that is lower energy than where I started. So I have an overall release of energy into the environment. What does that really mean? I have an overall more kinetic energy transformation than I do potential energy transformation. What I see is that my process releases energy in the form of light or heat, which is why some reactions like combustion are super heat generating reactions, because at the particle level and with the relationship between energy, where the reactants start in combustion with your hydrocarbon and your carbon dioxide, they have an overall higher potential energy arrangement than where they end as carbon dioxide and water. And that means that where that potential energy goes, because I can't just lose potential energy, right? Law of conservation of energy. What happens is it gets transformed into kinetic energy, which is then released as heat or light, still preserving the overall amount of energy. So then for endothermic reactions, these are energy categories for reactions. What we would say then is that the overall heat energy, when we look at the products minus the reactants, gives us a what number? A positive, the exact opposite, a positive number, which tells me that my process has an overall absorption of energy or gaining of energy. So what that really translates to is that my bond arrangement, my spatial arrangement of the particles that are products are higher energy, more energy being stored in that particular arrangement, less being observed as kinetic when I end than when I begin. So that's why some reactions, when you complete them, get off your phone. That's why some reactions, when you complete them, feel colder. You'll actually notice that it gets cooler around the container. That's an endothermic reaction. The system itself, the particles are gaining the heat and taking it from the surroundings, like your hand. So this hand boiler demo, is it an exothermic or an endothermic process? It's an endothermic process. It's taking heat from my hand and it's using it to transform my liquid to gas state. So endothermic and exothermic don't just go with chemical reactions. It also goes with physical processes as well. So you can think of the space above the lines in a potential energy diagram as the kinetic energy, the other half of your law of conservation of energy. And the kinetic energy that we tend to say it's heat or light is kind of what we see in chemistry. The kinetic energy forms that we see mainly are heat and light. So your quiz will ask you to read and diagram potential energy diagrams for a given generic reaction. So what we have here is read the following potential energy diagram and answer the questions. Is this reaction overall endothermic or exothermic? So what we say is the starting flat line is the reactants, the end flat line is the products, and the peak up here represents the activated complex. So when we compare the overall products end to the overall reactants beginning, what do we see? Are we overall gaining or are we overall losing potential energy? Gaining, we're overall seeing more potential energy being stored in the new arrangement of the bonds. So is this endothermic or exothermic? Huh? Endothermic, endothermic. Because I'm overall gaining potential energy. I'm storing more of that energy out of my set amount of energy. I'm storing more of it as potential in the bonds. Another way you can think about it is endo enter. Energy enters, endo enter. Okay, so that would mean that my value of heat would be a positive value. From products to reactants, I'm getting more in potential energy. Okay, we're taking it from the potential energy perspective. Okay. 2, what is my activation energy for this reaction? What do you have to do mathematically? You have to what? Is equal to what? Ooh, not quite. It definitely involves potential energy of the reactants. But what am I subtracting that from? The the potential energy of the highest point. So it becomes the potential energy of the activated complex minus the potential energy of the reactants, your starting point. So what would my values then be for this? I start at 20 kilojoules and I climb up to, so it becomes 100 kilojoules minus 20 kilojoules, giving me an activation energy of 80 kilojoules. You will never have a negative activation energy. If the whole point is that it takes energy to break bonds, it is literally impossible to have an upside down curve for these. I've had people draw and I'm like, dear Lord, make it stop. Don't ever draw an upside down energy diagram. It's literally not possible. That would be like saying that the process is so favorable, it's like a black hole of like spontaneity. It's like, that's not a thing. Okay. 3, what is the potential energy of the activated complex itself? 100. Sounds stupid. Even AP kids flip activation energy and potential energy as of the activated complex. They're not the same. Activation energy is the difference between the activated complex and where you start. But then you do have a set amount of energy that just goes with the complex, 100. Again, sounds stupid. 100% guarantee you 30% of you will make that mistake on the quiz. So I'm trying to address it now. Okay. And then what is the overall energy change for this reaction? We said it's endothermic, so we know it's got to be positive. What is it? Is equal to what? Overall change. 20, because what you did is you did the products minus the reactants energy to equal positive. And here sign does matter. You have to specify if it's positive or negative. 20 kilojoules gained in potential energy, okay, for this process. Pretty easy. Now, this is a sneak peek into unit like 8 or 9, which we might not even get to. But if you were to reverse a reaction, which by the way, some reactions are reversible, notice what changes. The enthalpy changes because you have a new start and new end, but what doesn't change? If you to reverse the reaction. Huh? The peak doesn't actually change. The height of the peak doesn't change. The activated complex doesn't change when you reverse the reaction. But the value of enthalpy and the value, okay, of your activation energy does change. That's something to keep in mind later when you read these graphs. And lots of reactions in this world are reversible. That's what makes it fun. So try out the next sample problem on your own, answering these questions. Sorry, just kidding. This is going to be our warm-up for tomorrow. That's a better idea. That gives me something to give you guys. So now let's talk about why I wrote H. So enthalpy is symbolized by the term H, and enthalpy is the chemical description, or you could say identification of heat in chemical processes. So the reason why I changed, okay, from just writing potential energy overall is that really what we're saying is that there's an overall heat energy change between this, the particles from beginning to end. And obviously heat energy in general, okay? Keep in mind that heat is not equivalent to temperature. Temperature measures kinetic energy. Heat is a form of kinetic energy. Temperature is the thermometer. Heat is the actual thing that you experience. So the general equation for H is, we already know, is that what we actually can say is the enthalpy of the products, the heat of the products, the energy of the products, minus the energy of the reactants. So we're kind of evolving our definition slightly to be more chemically accurate to the study of heat energy. This is how we actually write this. So obviously, if you're endothermic, you have a positive enthalpy value. An example of endothermic reactions are dissociation, the dissolving of an ionic compound. Okay. Exothermic is always negative. Examples, combustion is like your main one, like hands down guaranteed. Combustion is always going to be exothermic. We also can see endothermic and exothermic in physical processes. So what we say then is an endothermic process, a heat gaining process, and heat absorption overall would be going from solid to liquid to gas. The reverse would be exothermic, gas to liquid to solid. Now, if you're like, wait a second, I never feel heat release when I freeze my ice cube. Right, you don't feel it doesn't mean it's not happening. So that's a little less intuitive, but if you think about it, you're going from a liquid to a solid. You're going from a super chaotic high energy motion particle arrangement to a not condensed one. It would make sense that your system of particles is losing energy somehow. You just don't always feel it. Okay, so that's where I'm going to stop. Tomorrow we'll warm up with the energy diagram. And honors, you have an additional calculation and process on YouTube to learn before Friday for the quiz. You will be quizzed on that honors topic. All right, guys, good job.